Welcome back. This is on complex analysis. We are on the series of lectures on main results on holomorphic functions. This is session 3. It will deal with maximum modulus principle. Let us get started. So what does the theorem say? Okay. So suppose U is a connected open set. Okay. F from U to C is a holomorphic. Okay. Notice that since we are dealing with complex valued function, it doesn't make sense to talk about maximum. But we can talk about maximum modulus, that is modulus of the function and its maximum. So that's what you are going to say. Let A in U be such that modulus Fa is a local maximum. What does that mean? That is, there is an R positive, so that for all Z in BAR we have modulus Fz is less than or equal to modulus Fa. Okay. What do you want to claim? Then F is a constant. Okay. This is known as maximum modulus principle. Learn the version very well. Let us try to understand what it says. So, suppose I have F from U to C. As usual, we will be connected open. I don't know what to keep saying. Okay. And suppose it's a non-constant holomorphic. And holomorphic. Okay. Now you give me any A in U, any R positive so that BAR is contained in U. Okay. If I believe in the theorem, what does it say? It says there exists Z in U, Z in BAR, so that modulus of Fz will be strictly greater than modulus of Fa. Please understand. This will allow you to really understand what is the maximum modulus principle about. Many students have problem. That's why I keep repeating. So, why does it say that? Because suppose it does not, that means what? For every Z in, okay, I said there exists an R positive for given any R, right? Okay, given any R positive, so that BR is contained in U, there exists Z. Suppose this is false, what does it mean? That means there is an R positive, so that BAR is contained in U, but, okay, for every Z in BAR, I have mod Fz is less than or equal to mod Fa. But if I believe in modulus, maximum modulus principle, that will mean F is a constant. But our assumption is F is not a constant. Yeah? So, I claim this is an equivalent version. I'm saying these things so that you get used to this, because I find many students have problems with maximum modulus principle because it's somewhat counterintuitive when compared with real analysis in some sense. Okay? Right? Okay, so if I assume maximum modulus principle, I proved this equivalent version. Suppose F is a non-constant holomorphic function, so that this happens. Okay, right? I want to prove F is, okay, F does not have local maximum. Is that clear? Okay, suppose F is a function, non-constant holomorphic function with this property, then I want to say F cannot have local maximum, because if it has a local maximum, Okay, so this implies maximum modulus principle. Why? Suppose A is such that, okay, there is an R positive such that for all Z f mod f A, this happens. Okay, right? Suppose this such a thing happen, what have, okay, right? But then and f is not constant. F is not constant, but there exists A and R positive so that for all Z in BAR mod fz is less than or equal to fa, right? These are just logic thing. I just keep repeating, okay, because many of you may not have attended my courses on foundations, okay. That's why I have to repeat these things. Okay, you follow that, right? But then this contradicts our equivalent version. Why? Because it said, okay, for every r, this is also for every r positive, okay, so that br is continuous, I can always find a z in br so that mod fz is less than greater than fa. So this contradicts. Yeah, so let me repeat. Okay, it said that suppose there exists a so that mod fa is a local maximum, then f is a constant. So contrapositive is the equivalent version. What does it say? Suppose f is non-constant holomorphic, and then for every A in U and for every R positive BR is contained in U, I can find a Z in BAR so that mod FZ is greater than FE. Okay. So please go through, make sure that you understand. Yeah. So as you know, I always emphasize even before embarking on a proof of a theorem, we should understand what the statement is about. Try to analyze it and try to recast it, reformulate it in our own words, and look for contrapositive or some such thing so that you understand the real meaning of the statement. That's what we did. Okay. Now let's go through a proof. Okay, the main tool is the Gauss mean value theorem. What does it say? So by that, okay, so our assumption is BR is contained in U, right? Okay. Therefore, for any R1 less than R, let me just, instead of R1, let me write it something, maybe let us assume, as usual I am making choices, okay, choose an R so that BR is contained in this, and assume, I am assume for all Z in BAR, mod FZ is less than or equal to mod FA. Okay, I am just replacing R by capital R, okay, because I want to choose small r. Okay, now for any small r less than r, let us look at gamma r of t equal to a r e power I t 0 less than or equal to 2 pi. Okay, then what does Gauss mean value theorem says? Gauss mean value theorem says f of a is 1 upon 2 pi 0 to 2 pi f of a plus r e power I t dt. This is Gauss mean value theorem, right? What I want to do is I want to divide both sides by fa, but then that I can do only if fa is non-zero. So that makes us understand something better. So suppose fa is 0, then mod fa is 0, right? If and only if mod fa is 0, then what does it mean? Remember, for all z in BAR, mod fz is less than or equal to mod fa which is equal to 0. This implies f is 0 on BAR, right? Now notice that f is holomorphic and BAR is an open subset of this, non-empty open subset of this, on which this function is identically 0. Therefore, one of the immediate observations following the identity theorem, we know f is a constant. F is 0 on U because U is open and connected by identity theorem. Okay. So, in that case, we proved the result. Namely, what am I supposed to show? I am supposed to show f is a constant. Have I proved it? Yes, I have proved f is constant, right? So, we will as pause, review, proceed. So, we assume f a is not equal to 0. Therefore, what I have is 1 equal to 1 by 2 pi 0 to 2 pi f of a plus r e power I t dt by f a, right? Now, notice that this integrand is complex valued, and its the value of this integral is 1, which is a real number. Therefore, what we know is this means this is same as 1 by 2 pi of 0 to 2 pi of the real. Remember, if f is complex valued function, this is not this f, something else. If you want make it g is a complex valued function from a, b to c, and if I write g as u plus iv, then integral of g by definition from a to b is integral a to bu plus I times integral a to bv, right? Okay, therefore the real part must be equal to this. This is the real part of f of a plus r e power I t by f of a dt. So let us write f of a plus r e power I t by f of a as u plus iv. Okay, notice that a etc. are fixed, therefore I can think of this as a function of t, but doesn't matter. Okay, if you want, I can think of this as a function of u of t plus iv of t. Therefore 1 is 1 by 2 pi 0 to 2 pi of u of t dt, right? Next, notice that u of t, modulus of u of t is less than or equal to modulus of, this is a real part, right? This is a real part, therefore it's less than or equal to f of a r e power I t by f of a modulus. Okay, and remember f of a plus r e power I t, since r is less than capital R, this is in modulus is less than or equal to mod f a, hence this is less than or equal to 1, but this is already equal to 1. So, not u of t, sorry. Okay, therefore modulus of u of t is less than or equal to 1, right? Okay, now let's look at, now then 1 minus u of t. Okay, if I integrate between 0 to 2 pi, okay, dt, since 1 minus u of t, remember u is a real number, therefore in particular u of t is also less than or equal to 1. Similarly minus u of t, but I am just want to look at only u of t. So this is always greater than or equal to 0. And next, this is a continuous real valued function. Yeah, because f is holomorphic, therefore f is continuous, f a is constant, therefore this is continuous. So t going to f of a plus r e power I t by f of a is continuous and followed by modulus. So all these things, okay. Anyway, not modulus without that, okay. And real part is continuous, right? Therefore this is a continuous function, okay. And this is greater than or equal to 0, therefore I know it must be greater than or equal to 0, right? With this monotonicity of the integral. What is monotonicity of the integral? If f is greater than or equal to g are all real valued, then integral of f is greater than or equal to integral of g, where within the limits of integration, etc. I do not mention such things. Okay, right. But The integral is linear, therefore this is 0 to 2 pi of 1, which is 2 pi, minus 0 to 2 pi of u of t dt. But that, let us look at that by assumption, is 2 pi. Okay, that is also 2 pi, therefore it is equal to 0. You understand? So let us try to understand what I have done. So I have sent 0 to 2 pi of 1 minus u of t dt. Okay, this is must be greater than or equal to 0, but it is actually 0. But 1 minus u of t is non-negative continuous function. Right? Its integral is 0. Then that means u of t is 1 for all t in 0 to pi. Okay, this is a well-known result. Okay. So what is that? If f is non-negative, then integral of a to bf is greater than or equal to 0, and it is equal to 0 if only if f of t is 0 for all t in the interval. This is the well-known result which I am using. Okay, you can read it from my real analysis book or from my linear algebra book, where I talk about inner product, etc., etc. Okay, so I don't, if time is there, I will also give a proof if you want, but this is well known. You understand that? Therefore u of t is 1 1. Now let us look at what is u of t. U of t is real part of this fellow, f of a plus r e power I t by f of a, right? And modulus of this fellow, f of a plus r e power I t by f of a, this is equal to 1. Sorry, less than or equal to 1. You understand that? But the real part is already equal to 1. Okay, there if you write this fellow as u of t plus I v of t, that is f of a plus r e power I t by f of a, I write it as u plus I t. Okay, what do I know? This modulus is less than or equal to 1, but this modulus is already greater than or equal to 1. Therefore that means v of t must be 0. Right? See, modulus squared is less than or equal to, here modulus squared, okay, plus vt whole squared, but this is already greater than or equal to 1 plus something greater than or equal to 0. Okay, that shows this must be 0. You follow that? Okay, therefore f of a r e power I t by f of a must be actually u of t, but u of t is 1. Therefore that means f of a plus r e power I t is f of a for all t in 0 to pi. So understand, the proof is extremely simple, but except you have to be alert. Okay, therefore what do I have? I have an open disk and I have my a. Okay, this may be my bar, big R, and this is my small r. Okay, on this is 1, but okay, for each point here, f of a r e power I t, it is same as f of a, right? But then this is true for each and every r. For all r, this is true. Therefore f of a r e power I t equal to f of a for all 0 less than r less than capital R. When r equal to 0, it is f of a. Therefore it is true on. Therefore this implies f of z equal to f of a for z in b0 or bar. You follow that? Given any z, I can always find here. Okay, yeah. Therefore what do you think I have proved? Therefore I have proved f is a constant on the non-empty open set bar, which is contained in U, which is open connected. Therefore what do I conclude? By identity theorem, f is constant, namely f of z is f of a for all z in u. Okay, so we proved the result. This proof is exactly as in my book. Please go through it. This is perhaps the simplest proof I could ever find for maximum modulus principle. Okay, learn that well. As you can see, it's very easy. Okay, you have to be alert. That's it. As far as I could see, that's a major idea. Okay, all ideas are simple except I would use mean value theorem. Okay, you use mean value theorem, divide both sides by fa, provided fa is non-zero, etc. Okay, after that be alert. Use a basic analysis, you get the result. Okay, right. So, but notice that because of real analysis, we are always interested in something interesting. Suppose this is, remember, this is for any open connected set U, right? Suppose imagine the following situation: U is bounded and open, of course connected. Okay, you understand that U is bounded, open, and connected. Then if I take U closure, that will also be bounded and closed. It will be bounded, but it will be now closed. Therefore, it's compact, right? Now suppose I have a function f which is continuous on U closure, but f is holomorphic on U, right? Then z going to mod fz is a continuous real valued function on the compact set U closure, right? Therefore, it should attain its maximum. Where do you think it will attain? The answer is clear, right? So that is the next corollary. Hence is compact by Haney Borel. Let me see. I just shared the screen. Yeah. See, I knew I do such mistakes. That's why I'm afraid. Let U be a bounded open connected set. Note that U closure will be closed and bounded and is compact by Haney Borel. Okay. And suppose f from U close to C be continuous, then okay, z going to mod fz attains a maximum. At some point of U closure, right? But what do you expect? It cannot be attained in U. Are you following? Yes. Therefore, where should attain? And U. This is the boundary of U. Notice that even if it is constant, this result is true. If it is constant, then okay, it will be, if f is constant on U, it will be constant on U closure also. You understand that, right? Therefore, the maximum is attained on the boundary is still a correct statement in whether or not f is constant. So the important case is if f is non-constant. Okay, so if you want to assume it's non-constant. So yeah, and I forgot again. f to z is non-constant holomorphic. Right? The I already explained the proof. Okay, z going to mod fz is a continuous real valued function on the compact set U closure. Therefore, there exists z naught include U closure, so that modulus fz is less than or equal to modulus fz naught. This is true for all z in U closure. Right? Now, can z naught belong to U? If it did, what does it mean? In particular, for every z in U, I have modulus fz is less than or equal to f of z naught. That means the modulus of f attains a maximum at z naught, a point of U. Therefore, by maximum modulus principle, okay, f is a constant on U, and hence f is a constant on U closure. Because if z belongs to U closure, there is a sequence zn from U, so that zn converges to z. But f is continuous, therefore f of zn will converge to f of z. But f of zn are all constant, therefore f is constant. Okay? Is the proof clear? Okay. But remember, this is a corollary. So whenever I say it's a maximum modulus principle, do not think of this corollary. You should always think of the version which you said. What did we say? If I have an open connected set and I have a holomorphic function, okay, if mod f attains a local maximum at a point A inside U, then f must be constant. In other words, if f is non-constant holomorphic, you give me any point A in U, then I can find for any open disk BAR contained in U, I can always find a z so that mod fz is greater than mod fa. That is the equivalent version, contrapositive version we said. Please understand. Okay. So we will derive some from this another version, what is called minimum modulus principle. But meanwhile, so we have proved a maximum modulus principle. Then natural question is there any analogous of minimum modulus principle? So naively, what should I expect? I should expect if minimum is attained, that is minimum mod f is attained inside U, then f must be constant. But think carefully, that cannot be true, because what is the least minimum for modulus fz? It could be 0, right? So if the holomorphic function f has a 0 in U, if it's a non-constant function, then this will be violated. Do you understand? I want you to think rather than simply accepting. Okay, this is very easy, right? Let us look at f of z equal to z and the unit disk. Okay, then what is the minimum modulus of f? 0. That is attained at the origin. Okay, center of the disk. Yeah, so you have to be slightly more careful. How will you do that? Think about. We will come back with the minimum modulus principle in the next session. Take care, stay safe.